So with this lecture on MPC, we have actually finished all the theory I had prepared for the optimal control part. But now we're going to have a few lab sessions to see what kind of applications we can tackle using the tools that we have covered in theory. And today I wanted to give you something a bit different from what we have seen this far, which is working with a differential drive robot. So it's a much simpler robot than the manipulator we have worked with so far, but it's still interesting. And the topic I wanted to discuss today is doing obstacle avoidance with differential drive robots. And everything we're going to see basically today with about obstacle avoidance, you can quite easily use it also for doing obstacle avoidance in 3D with the manipulator. It just becomes a bit heavier in terms of computation, but the key ideas are going to be the same. So I think it's useful. If you want, and you have your laptop, you can open this Python notebook, which is inside the org folder, optimal control, Casadi. And it's called diff-drive obst avoid. It's the only notebook inside that folder. If you don't have that folder, you need to update the repository. So as usual, you can either do a git pull, or you can reclone the repository from scratch in case git pull doesn't work. This is a notebook. So we have a differential drive robot. We want to reach a target with this robot. And we have collisions, we have obstacles in the environment, which we want to avoid colliding with. And for the moment, we're going to assume that these obstacles are static. Later on, we can discuss how to extend this to dynamic obstacles. So the model of a differential drive robot, in case you have never seen it, is quite simple. We model the state of the robot as its 2D position on the plane. And we use one angle, theta, for representing its orientation. The control inputs of the robot are its linear velocity and its angular velocity. So the system is underactuated because it has 3 degrees of freedom, but only 2 actuators. And in particular, it's pretty clear, I think, the thing that the robot cannot do is to move laterally. It can only move forward, or it can rotate, but it cannot move laterally because, well, it's a wheeled robot. Its dynamics is nonlinear, but it's very simple. So the velocity along the x-axis is given by the velocity control input times the cosine of the orientation theta. The velocity in the y direction is given by the velocity control input times the sine of the angle. And, well, the angular velocity is directly equal to the control input omega. So we can write this dynamics in Casadi using this code. It's just code for the expressions that we covered a moment ago. And now we can start defining what is the trajectory optimization problem that we want to solve. And I'm going to start with a very basic definition that is not considering obstacle avoidance, just to get started. So we have a desired state that we want to reach in the environment. So we're gonna use a terminal cost for representing the fact that we want to reach that state. And the running cost is simply penalizing the use of the control inputs, which is always a good idea, regardless of whether you care about it or not. To have some quadratic penalties on the control input is always good because it acts as a regularizer for the optimization problem and makes convergence easier. So I always have it in my control problem. The constraints are simply the dynamics of the system, and then we have some bounds on the control inputs because we don't want them to go too high. So this is the problem written down in Python code. Okay. So we are using the same Casadi library that we have seen last time. So you should start to be a bit familiar with it. We start by defining all the optimization variables. We have one variable for every state in the horizon, one variable for every control inputs in the horizon. The control inputs are bounded. So we specify the bounds umin and umax. We fix the initial state to the given value. And then the running cost is simply the summation of quadratic cost on the control inputs scaled with this weight WU. We have the dynamics as a constraint. And we have a terminal cost, which is penalizing not reaching the desired state at the end of the horizon. And this comes without any weight. Because since we have a weight for the cost on the control inputs, we don't need a weight for the terminal cost. We can just scale WU to have whatever ratio with respect to the terminal cost that we want. So it would be redundant to have a weight also for the terminal cost. So we say that this is the cost that we want to minimize. We create the solver, which is the usual IP opt, specifying that we don't want it to print anything. And that's it. This is where we define all the parameters of the problem. So the time step is going to be 0.1 seconds. The horizon is 25 time steps. The initial state for the robot is just 0. WU, we set it to 10 to the minus 4, so it's quite small, which means that we care much more about reaching the terminal state, the desired terminal state, rather than minimizing the control inputs, because of course the two things are in conflict. The bounds on the control inputs are plus and minus 2. And when we're gonna draw the robot in the plots, we're gonna draw it with a ray of 0.1. So we're gonna draw the robot as a circle. This is actually the function that we define for drawing the robot. It basically draws the robot as a circle plus a rectangle. So we understand its orientation. So when we draw the robot with a 0 angle, it shows like this. Whereas if we draw it with an angle of 45 degrees, it shows like that. And this is the function that actually solves the problem. So we call the function we defined above for creating the problem. And then we simply call the solve method. And we have these two lines for retrieving the solution into an NumPy array. And then we plot the solution just to visualize what trajectory the solver optimized. So here, as usual, I created these sliders, which allow us to move the desired state for the robot to reach. And you can see as I move the desired states, the plot gets updated, and we can see in real time the solution computed by the solver. If I change the desired final orientation, you can see that the trajectory changes shape. So here actually the robot is moving forward until this state here, and then the final part does its moving backward. If I change the orientation in the other direction, I can see a similar behavior. We have a first part moving forward and then a second part of the trajectory moving backward. So I can move the desired state very far to the top right. And if I push that to the extreme, which is to the state 4, 4, what happens? And why? Or maybe it's not clear. The red circle represents the desired state of the robot, whereas these black circles represent the computed trajectory, and the blue represents the initial state.
We can't get reaching the maximum.
Yeah. So the reason we cannot get there is that we have reached the limit of the control inputs. And even if you do just a quick math in our heads, we know that the control inputs limits were 2 for the velocities. So the robot can move at most at 2 meters per second. And the horizon was 2.5 seconds. So in 2.5 seconds, the robot can do at most 5 meters. No, sorry, 10 meters. No, 5 meters was correct. 5 meters, and now we're asking it to reach this point, which is more than 5 meters away from this point. Because we are basically, this is a square of side 4. So for sure the diagonal is more than 5. I cannot do that math in my mind, but pretty sure it's more than 5. So if we move it there, it's too far and it doesn't work, but that's okay. I mean, that should be expected. Let's look instead what happens if I move the desired final state there. So if the desired final state is there, the solution is okay. It's a bit convoluted. You need to move backward, then forward up until here, and then the final part is also done backward, like a parking maneuver. But then if I move the x-axis of the final desired state to 0, so that it's right on top of the initial state, the solution is basically to stay still. It doesn't move.
Hai penalized too much the width, cioè le tones, so it's better to stay to.
You penalize too much the control inputs.
Yeah. It's better to stay still than to move to the desired position.
we can see if that's the case. I'm able to find the point where the hyperparameters were defined. So we can set this to 0, right? We re-execute everything. No, it's not that. Why is the solver telling us that the optimal thing to do is to stay still? It's related to the under-actuation of the system. So we said that the system can only move forward or rotate. It cannot move laterally. In which direction should it move to get closer to the desired final state in this case? It should move laterally, which it cannot.
So he is like over constrained.
No. It's a local minimum. That's what you wanted to say?
I suppose like if I have 0 arrow on the x and theta axis, then moving from that point, every point I'm just adding some arrows. So.
Yeah, basically that's it. So anything the robot can do here locally, it's gonna make the solution worse. Because if it moves a bit forward, then it's getting further away from the desired state. And if it rotates a bit, also it's getting further away because the desired orientation is 0, which is exactly the one it has right now. So staying where it is a locally optimal trajectory. So we always have to remember that gradient-based optimization solver is not a magical oracle that can solve anything. It's just finding a locally optimal solution. And that is a locally optimal solution. A very bad one, but still locally optimal. If we just change the desired orientation of the terminal state a little bit, then it works. You see. But if the final desired orientation is the same as the initial one, then we have this local optimum. Okay, so how do we overcome this issue? Any idea? I don't want to change the desired target because that's the target I want to reach. How do we help the solver find a better solution?
Maybe we can start with the force it to go forward a bit initially.
Yeah, I think that's kind of the idea. We need to give it an initial guess that allows it to exit this locally optimal solution. And actually, we have many options for doing that because any perturbation of that initial state, I think, would work for allowing the solver to leave this, to escape this local minimum. So for instance, we could just move forward the position on X, or we could change a little bit the angle Instead of having an angle of 0, we could give an initial guess with an angle which is 10 to the minus 4. That would also be sufficient. And so we are not changing the problems that the solver has to solve. We are just changing the initial guess for starting the search process. That is sufficient for escaping that local minimum. So what I did here is that after creating the problem with the same function used above, I'm using this method, which is, I think it's the first time that we see it. It's called setInitial. And it's a method that Casadi gives us for providing an initial guess to the solver. And we can provide an initial guess for whatever variable we want. We can initialize all variables or even just a subset. And in this case, for instance, I'm only initializing the state variables. I'm not initializing the control variables because that's sufficient actually for what I want to do. And I'm initializing the state variable to be equal to the desired final state and the desired final orientation plus a very small perturbation of 10 to the minus 4. I could perturb it with whatever I wanted to. Or I could probably also perturb X and Y. Yeah.
When perturbing all the k states and not just the...
I don't know. I just tried this, it worked, and I stopped trying. If you want, you can try perturbing only one of them. It may be sufficient. I mean, this is an easy local optimum to escape. So I think that whatever you do is going to escape it. So we can check now when we reach that desired state, the solver doesn't seem to suffer at all. It's able to find a solution which is actually very similar to the one it was finding before. And it works. And it works super fast as well, because every time I'm moving the slider, the solver is recomputing a solution from scratch and updating the plot. So everything is happening so fast that it's almost real time.
The initial guess are chosen randomly?
No, I decided to set the initial guess to be equal to the desired state plus a very small perturbation on the angle.
So here I'm only perturbing the angle.
Yeah. I guess it could work even if you perturbed X, the X direction, but I haven't tried. But what's nice with the Python notebook is that you can just change, rerun, and try things on your own, because we don't have time together to try everything. Okay, so far we have just optimized a trajectory to reach a state, but we haven't talked yet about collision avoidance, which is the main thing I wanted to discuss. So collision avoidance, of course, the way we formulate it is going to depend on the shape of the obstacles that we want to avoid collision with. So let's start with the simplest obstacle possible, which is a circle. So if the obstacle has a circular shape and the robot has a circular shape, well, in this case, the constraint is going to be very simple. It's going to be a quadratic constraint. So we know that given a circle with center Cx, Cy, and ray Ro, a point belongs to that circle if it satisfies this inequality here, which is basically saying that the distance between the center of the obstacle and the point is smaller than or equal to the ray of the obstacle. So if we want to check whether the robot is in collision with the obstacle, since also the robot is a circle, we need to check whether the distance between the center of the robot and the center of the obstacle is smaller than the summation of the radius of the obstacles and the radius of the robot. Is everything okay with that? So this is going to be an inequality constraint that we need to add inside our optimal control problem definition to make sure that the robot never collides with the obstacle. So here we define the parameters, which are the usual ones. And here we create the optimal control problem with the extra collision avoidance constraint. So actually the extra code is just these 3 lines. So I'm doing a loop over all the time steps from time 1 until time n. And for every time step, I'm computing the distance vector between the robot state, which is the first 2 variables of the state vector, minus the obstacle position. And then I'm computing the distance, which is the square root of first dimension to the power of 2 plus the second element of the distance vector to the power of 2. And I'm imposing that this should be greater than or equal to the ray of the obstacle plus the ray of the robot. That's the same equation that was written below, above. And then I just plot stuff. Nothing special. Just a quick note. I didn't impose this inequality constraint on the initial state. So I decided to start from time step equal to 1. Why?
I'm assuming that I'm not colliding the obstacle in the first place.
And even if I was colliding with the obstacle in the initial state, can the solver do anything about it? No. No, because the initial state is fixed. So it doesn't make sense to add constraints on the initial state because it's already maximally constrained. We have the constraints that x0 should be equal to something. So we cannot add inequality constraints on top of that. So here it is, the new problem with the obstacle. So the obstacle is this black circle, and we can move it around with the slider. And we can see that as soon as I move the obstacle, so if I move the obstacle here, the solution doesn't change because the obstacle is not colliding with the current solution. As soon as I move the obstacle close enough to the solution, then the solution changes, of course. And the solver figures out a new solution that doesn't collide with the obstacle. And then I can keep chasing the solution, and I can see how it changes when I move the obstacle around. I can also change the size of the obstacle. I can make it bigger or smaller. Okay, and here, look, I found out another locally optimal solution, which is pretty bad. So it turns out if you put the obstacle exactly, it seems to be exactly in the middle. So along the segment that connects the starting state and the final state, at that precise distance, the solver finds this solution here which is not very good, which doesn't reach the target. And if you make the obstacle bigger, which actually should make the problem more difficult, the solver finds a better solution. So that can happen when you're working with optimization. Maybe a more difficult problem makes the solver find a better solution than an easier version of the same problem. So let's check what happens if I move the obstacle on top of the desired final state. And in this case, I would say that the behavior of the solver is very reasonable. It just cannot reach the final state. It gets close to it, but then it stops. Let's see what happens instead if I move the obstacle on top of the initial state. Error. And to a certain extent, it's quite reasonable that if the obstacle is on top of the robot in its initial state, it doesn't work. But actually, we took care of not having the obstacle avoidance constraints on the initial state, right? Because we said that that wouldn't make sense. So why is it still failing? Well, if you look at the error message, it says none detected. So you know what none means? It's not a number. It's typically what you get when you divide by 0. And it's weird that we get none. So let's go back to the definition of the constraint, which is this one. Is there anything that could go wrong when evaluating these constraints? Yeah, you should always be careful when you formulate your constraint to make sure that they always produce a valid result. Like when you take the square root of something, well, that something better be positive. And here, what we have inside could be 0. Square root of 0 is undefined, and especially if you then take the gradient of that, it goes to infinity. So it would be better not to have the square root inside that constraint definition. Can you think of an alternative way of formulating that constraint which does not require the square root? Can I?
Could you ask your question again?
Give me an alternative equivalent way of formulating the constraint without using the square root.
Be the absolute value.
The absolute value of what?
Of the argument of the square root.
Okay, but if I take the absolute value, well, first of all, it's unnecessary because it's the sum of 2 squares, so it cannot be negative. But then it's not equivalent to the square root.
Okay, maybe use the normal squared and then split into constraints with plus minus square root of a obstacle plus a of. That should be always be positive or always be negative.
Plus minus square root, but then you're still using the square root. We want to avoid using the square root.
Yeah, but the obstacle and plus a of should be, I mean, always greater than 0. If I have not that, I don't have an obstacle of 0 radius.
Okay, then I didn't get your suggestion. Can you repeat?
If I, instead of the square root of the distance, I use the norm squared.
Okay. So no square root, basically.
Yeah. But then I should use the square root on the other side.
No. How do you remove the square root? What's the inverse operation of the square root? Power of 2. So you don't need the square root. You need the power of 2.
Yeah, but the distance is the Euclidean norm.
Yeah.
And the Euclidean norm without the power as well. No, yeah. Okay.
So if you take the power of 2 of both sides, since they're both positive, well, they're both non-negative, then you didn't change anything, basically. I mean, you get an equivalent formulation of the constraint. So what we can do is that we can get rid of the square root here and simply take the square of the right-hand side. That's an equivalent way of expressing the same constraints, but it's just much better for a numerical solver, because this will never run into problems with nuns, for instance. It's always defined, its derivatives is always defined. Like quadratic functions are the best for solvers. So I can redefine the problem in this way, reevaluate this, and now I can move the obstacle again on top of the initial state, and it works. I mean, it's of course a silly solution, because, well, we are asking the solver to solve a stupid problem, but at least it doesn't fail for numerical issues. So in general, always try to find the way to formulate your constraints that is less likely to lead to numerical problems. So if you can avoid using square roots, for instance, it's a good idea. And if you use them, well, make sure that the argument is always going to be positive. Another option could have been to add a small regularization inside the argument of the square root. So square root of the distance plus 10 to the minus 8. That way it never gets 0. Okay, so we already answered the first 2 questions. Third question, what happens if you check collisions in between time steps?
Do you mean in between them steps?
So at the time instance that's in the middle of 2 time steps.
Slightly compenetrate the solution.
Hmm?
I could maybe compenetrate the solution by something, because I am evaluating it when I am half time step ahead.
Yeah. So actually we can even do this visually. It's not so clear, but if you look close enough, I think it's pretty clear that the robot is avoiding collision at the discrete time steps, which corresponds to the drawing of the robots in the plot. But if in your mind you connect the time step with a continuous trajectory of the robot, you can see that there is a collision. And that's always a problem that you have to keep in mind, that when you do trajectory optimization, you only ensuring constraints and also the dynamics, by the way, at discrete time steps. You don't have any guarantees on what happens in between. And here, since we are using a very large time step of 100 milliseconds, well, this becomes more of a visible problem.
Increasing the time step.
We have different ways of solving it. So here, I just basically did with the code the same thing that we just did visually. And I've plotted the robots in yellow at the point in between time steps where there was a collision detected. So you can see that's really, yeah, there is a collision there. Then how to solve this? We have different options. So one way is what you just suggested, which is use a smaller time step. Well, if you use a smaller time step, then of course it's going to be closer to continuous time constraints. But for instance, if you make the time step 10 times smaller and you want to maintain the same horizon length, you need to increase the number of time steps by 10, which is going to increase the computation time by at the very least 10, maybe even more. And you haven't really solved completely the problem, you've just mitigated it. You've made it a bit less obvious. So there's still going to be potential collisions, but it's going to be smaller in terms of penetration. Any other idea?
I could increase the margin, simulate a bigger obstacle.
Yeah, that's another option. So if your obstacle has an array of 10 centimeters, well, you can say it's 11 or 12. You add a bit of a safety margin, and you hope that that margin is enough to compensate for like interpolation constraints. That doesn't come with any extra computational cost. However, it's hard to know exactly how big this margin should be. And if you make it too big, then it's going to be potentially conservative. Imagine that the robot needs to pass through a door which has a size which is slightly bigger than the robot's. Then if you make the margin too large, the problem becomes unfeasible. And so if you make it too small, maybe it's, well, you don't achieve the real continuous time collision avoidance. So it can work, but it has some pros and cons.
Could I add more constraints on the pair constraints to the solver?
Yeah, that's a third option. So you could maintain in the same time step, so the same number of decision variables. You could just add extra constraints to say that you want like the average state between time k and time k+1 to be collision free. So that is a bit like decreasing the time step, but without paying all the price of increasing the number of decision variables. So it's a bit better maybe. There is a fourth option, which is the best one, which is a bit less obvious maybe.
I can make the time step dependent by the distance to the obstacle.
Maybe. I've never thought of that. Seems complicated. Any other idea? Okay, so the first three are the ones that we just discussed, that you came up with. The last one, which I think is the best, is that you could check collision instead of just between where the robot is now and the obstacle. you could take the convex hull between the current robot position and the next robot position and check collision between this convex hull and the obstacle. So you would make sure that the whole continuous time interpolation of the robot shapes between now and the next time step is collision free. So I think that maybe drawing it would help. Like if the robot is here now and the robot is going to be here at the next step, imagine these two circles are the same size. You can take the convex hull, which is this thing. It's basically a capsule. And if you check collision with using the convex hull, then you can be sure you have continuous time collision-free motion.
Why convex?
It's called convex hull.
Okay.
It's that's the geometric name when you take two shapes and you take the sets of all the points that you could obtain as a convex combination of a point from this and a point from this.
And so you can check the collision.
Yeah, basically in this case, it would be like checking collision with this rectangle, this circle, and this circle. Because if you take the union of this circle, and this rectangle, you have the convex hull of the two circles. Of course, I need to explain you how to do collision checking with polygons, which is the next topic discussed in this notebook, but we ran out of time. So we're gonna stop here for today and we're gonna continue with this notebook on Monday. Do you have any question before we stop? Okay, see you on Monday.